So Earth's climates arise from an interplay of long-term trends. So we can look at trends, and that's what more of our climate modeling is. It's trending. We can see this trend and we try to model the projection of the trend, but it's very difficult. We can look at atmospheric changes on local scales and then try to see how that may affect the trend. And we can look at extraterrestrial factors like sunspots. So they calculate the sunspots. We can see the distance. We can calculate the orbit of the Earth. These things they try to put in a model, but it's very complicated. So climate sensitive refers to global temperature change in response to specified climate forcing. So what is the thing pushing the climate? And that's what they're trying to find out as a climatologist. So you go to school for 4 years, what are they trying to look at? They look at more than just carbon. Carbon's a big one, but there's lots of other things. So a climate forcing is an imposed change on the Earth's energy balance caused by examples, changes in solar activity, or the change in atmospheric CO2. So we're going to start to look at that in a little bit more detail. So long-term trends are determined by the orbit of the Earth, the Sun and the Moon, the ice ages, and the warm age cycles. So here we see a picture of what the Earth is projected to be looked at because we use trends. So if we can understand the past, it helps us to trend what's going to come in the future. And this is what they do with the ice core sample. So they go in, they drill, they read the ice core samples, they're able to determine the CO2 present at different points in history, and they can calculate the temperature due to the isotopes of CO2. So they're looking at the radiation and the isotope loss of the CO2, and that's how they can tell what the temperature was at that particular point in time. So this is where the ice age covered. So in this point, 18,000 years ago, most of what we know is the northern hemisphere was covered in ice. Now we're living at a very nice climate, but the question becomes, is it going to get warmer or cooler? So a Russian scientist named Mininkovich was the first one accredited with calculating what he called, or people call, Mininkovich cycles, which is basically the eccentricity, or as I said, the Earth is not in a perfect ellipse around the sun. It moves, okay? And every 100,000 years, it has the furthest point away, right? So the closest to the sun and furthest away from the sun in a 100,000 year oscillation. Okay, so here we go. He can do that. So orbital gravitation facing the sun, the moon, and other planets affects this. So our scientists can now calculate this with computers. This is sometimes called the precession of the equinox, meaning that not only do we go closer and further away from the sun, the moon does the same thing. The tilt of the Earth also changes and wobbles. So all of these things puts the distance and the radiation that comes in and is reflected from the Earth, because as this tilt, more or less energy enters the Earth's atmosphere. So the cycle extremes are termed the phenomenon closest to the sun, which causes warming, and the aphelion furthest from the sun, which causes cooling. So the tilt, or the obliquity cycle, very hard words, increase the obliquity, the warmer summers and the colder winters. So depending on that tilt in relationship to the oscillation gives us temperatures also in relationship to the present parts per million of carbon. So the increasing phase is normal cools the climate, and as we get closer for reflection, meaning that there's less tilt, the sun, it doesn't reflect and we get warmer. So the wobble, or known as the precession of the equinox, driven by tidal forces. So the moon, as the moon gets closer or further away in its precession, makes the Earth tilt in this wobbling state. So here we got, and people can do that. That happens every 13,000 years. So there's a cycle of every 100,000 years around the sun. Every 13,000 years, the tilt of the Earth changes, right? And every 9 years, I think it's 9 years exactly, the moon is different. So these all affecting what's going on. So here we go, and we go back to this very famous graph. This is the ice core samples. So they look for they can go back currently 800,000 years and look at our temperatures. So here we can see different periods of the Earth, and some of them are interesting periods for Europeans here. I know when I was in school in America, we did learn some things about Europe. We learned about a warm period in Europe. I think it was called the Renaissance period, right? It's a famous period. Did you know that the temperature during the Renaissance period was 3 degrees warmer than today? You've been told if the temperature of the Earth increases by 3 degrees due to global warming that we're all going to die, right? Is it interesting that it was the same temperature as the medieval warm period? You see that warm ages? Renaissance period? But you know that one that's called the Ice Age, or one that we call the Little Ice Age? What do they call that? The Little Ice Age? That was the Dark Ages? When they had the plague and all that? Because they didn't have enough food? It was 3 degrees cooler than it is today. You know what's really interesting? When it was 3 degrees warmer, they grew grapes not in France. They grew them in England. Yeah. When it started to cool, they moved the grapes down. You know what's really interesting now? People are starting to replant the grape. Those are Roman grapes, right? The vineyards. They're starting to replant those back in southern England. So as a climate, the climate can change. And as a designer, can we work? I may not be able to stop the climate from changing, but in my own region, I can work with plants that are adapted to particular climates. So if it's getting warmer, I can plant more warm adapted plants here that are able to take drought. They're able to cope with that, right? And if it's going to get colder, I can bring in plants that would cope with that also. So we can put our head in the sand, and or we could look through history and try to predict with a trend what we might do as agriculturalists so that we can have food or feed the world. So here's a little bit closer, 600 million years of change. And there we see our average global temperature in over 600 million years. We can see it changing, right? Do you notice that the CO2, if we went back to that time period, was very, very high, but the temperature didn't change? Seems strange. The CO2 was very, very, very high, but the temperature didn't change. So we have climatic factors that we can look at. So if we bring all this together, we have a 100,000 year sun oscillation. We have a 41,000 year obligatory, and we have a 26,000 year wobble, and they all overlapping like this. Based on maximum science. So here we go. Reversed Arctic cooling. So if we start to look at this, in the past 2,000 years, Earth's orbit has moved 1 million kilometers further from the sun. And then we'll go away. So that there's some relationship to temperature on the Earth and distance to the sun. Earth's magnetic field is generated from its internal iron core, not by external forces. So the magnetic field shifts and they're irregular. So when we look at the ice core sample, there's no regularity to the shift of the Earth's magnetic field. So every 300,000 to 1 million years, it would shift, but we don't know exactly. So pole shifts can take 1,000 years for the actual complete pole shift during the ice core sample readings. But when we look at the temperature effect, we don't see anything related to pole shift. So if the pole shift or the magnetic shift, there seems to be nothing related to temperature, right? So our climate change. So that's a good thing. But atmospheric changes do play a role. So when they go back and they look at those temperature shifts, most of the time they find them due to some type of atmospheric change. Volcanism, today we're living in a time of industrial pollutant, so we put pollutants into the air. And any type of land use changes, because we actually started to change our agriculture, right? We were hunters and gatherers. And then we started to turn into agriculture. So to get agricultural fields, what did we have to do? Cut down the trees. So cutting down large areas over the last, how many thousand, 10,000 years of tree cover to put in agriculture, burning that, releasing the CO2. These are also things that is very difficult to model. So if we have this atmospheric composition, again, coming back to the concept of there's this greenhouse that we live in. And what is the effect of all of this on our greenhouse? That's the interesting point. So here is our atmospheric composition that we can measure going back to the 1750s to 2000. And in that period of time, just that little piece of time, the atmospheric CO2 increased by 30%. Mostly believed due to humans burning fossil fuels. That's a big impact. What is it going to do? That's the real question. Is it driving that temperature change? Or is it going to make it cooler? Is it going to make it warmer? And right now, I think it's a little bit of a toss-up. Which one? Probably we might get warmer, and then it could drop us into the ice age. If we were to look at the historical trends of the past ice ages, every 10,000 years there's an ice age. We're overdue. If we look at a trend, we're overdue for our ice age. Which could come. So interesting. So here's our atmospheric composition today. The carbon dioxide, nitrous oxide, and methane are going off the chart, all right, due to human-related industries, okay? And if we break those down, we can look at the emissions per sector. So what sectors of our economy are actually driving these releases? And if we look into, for us, that's interesting, we can look at how we have a direct impact if we produce agriculture. Agriculture does around 30%. So if I can look at that, that's a low-hanging fruit for me. That's something that I can do something about. I can change my agricultural practices. I can, over time, when I first bought Raktamachat, I had to get a tractor. It's so degraded, I need a tractor to help fix it. But over time, we hardly use a tractor anymore. So I had to use fossil fuels to try to fix the problem. But over time, we would hope with permaculture that we would be able to say maybe in the short term, utilize fossil fuels to try to fix the long-term effects that we've been doing. So changing our practices, becoming more efficient. So atmospheric aerosols were a very big problem. The sources of aerosols were coming from deserts and volcanoes, and we also get them from fossil fuels and biomass burning. We can see here that almost 50% of what we consider aerosols that are controlling that reflection, right, are from natural occurring forces. So if a volcano goes off, who can predict the next volcano, right?